Hey everyone, and welcome to the Information Bottleneck podcast, the podcast that squeezes out all the relevant information. And today we have a very special guest, Nadav Timor. He's a researcher, and we also work together at One AI. Actually, all of us work together. And I actually interviewed both Ellen and Nadav. And so, yeah, welcome, Nadav.
Thanks so much. Thank you for inviting me.
And today we will go and we will talk about a lot of different topics. We will start with news, and then we are going to talk about speculative decoding and how you can accelerate your inference. So, what did you hear from the last week?
I'll say the first thing that came to my mind was the Oracle deal as an ex-Oracle employee, right? I'm not super surprised when I see these because while I was at Oracle, I saw, that partnership, like even Stargate before the media was kind of, knew it by that name. But also Oracle tends, and even OpenAI tend to leave public breadcrumbs about deals like this impending. And so that's shocking investors, but anybody who looks at GPU prices, I think, will not be surprised right now that OpenAI goes to them.
Yeah. So, right. And also we saw Bastem, a company, a startup that basically wraps VLLM, and they raised funds at like more than 2 billion valuation. That might also reflect that trend.
Okay, but I must admit that, like, so VLLM, right? Whoever knows VLLM is like a framework that you can basically run models, a scheduler, and synchronize between different APIs calls to LLMs, and a lot of things. But at the end, I'm not sure like how it can make money. you know, it's really nice. I'm really pro open source models, and yeah, we should make everything open source and live in a world that everything is out there. But how you can make money from that, right? How you can make money from a library or from a framework? This is the main question. And I heard it a lot, like there are so many startups that are starting like that, right? Like we have a package that is doing this or this, and even if everyone are using it, it's still unclear how you can make money out of it.
You have downstream applications, right? It's a good question, and I think everybody in space is still like trying to figure out. But you have downstream applications that don't do inference in house. You have, for example, Cursor and others. They have a lot of traffic, a lot of many tokens to buy, and they are doing it with other providers. And Bayesian is just one of them. You also have Together AI, and they were the first company to reach $100 million. I don't want to say ARR. I don't know if it's like returning or not, but whatever. They had like crazy revenues, and fireworks. They are also like in that space. FAL, and they all seem to have like high valuations, but it doesn't, as you said, like it doesn't really mean that they have the incomes. But from what I know, from like investors and so basically they are doing well, and also they are growing organically, which is kind of surprising.
Yeah, and one thing you talked about Cursor, and I always tell people that Cursor and Windsurf and these code IDEs that allow you to select from any of the models that OpenAI, Google, and Anthropic, these big three, provide, the closed source models, that's powerful because they're interdicting the demand to pay $20 a month or per token, whatever it is, to OpenAI, still delivering OpenAI's or Anthropic's or somebody else's service in actually a better package, right? This like prosumer, pro level IDE. So this is really smart. Whereas together, Fireworks and the rest of the per token inference engines available through the hyperscalers with tiny exceptions like Azure's OpenAI. All of these are open source models only, and you can be the cheapest and best provider of DeepSeek. Sorry to take shots at Meta here, but Llama, Mistral, of Quen, but you're not beating those big three that I just said. And so I'm bullish on the idea of like its importance for everybody to make inference engines better, like VLLM and SGLang, where the community has basically admitted that with some exceptions, these are the best paths forward. But I'm very concerned about the core concept of, especially for public cloud, of like that being a sustainable business model. And even, the way that you could also try to monetize, which is doing the dreaded like adding ads or something to, your output tokens, is horrifying to imagine. But I'll say one last thing on this, which is Weights and Biases is a success story about how you can go from huge open source adoption to at least getting bought out by CoreWeave and making money in some. I think they might have been profitable before they were bought. I'm not sure, but I wouldn't be surprised.
Yeah, I think this is actually it's a good point, because I think like Cursor and all these ideas, I think that they give you something that like the models don't give you, right? Like it's much easier to go, and we see that like now like the recent I don't know, the recent OpenAI model is better than the recent cloud model, so I will just replace, right? I will just write, instead of ChatGPT, I will write like some other model. But to go to another idea and to go to another software that like coding environment, it's much harder, right? And it's much easier to lock you in this environment. So I think it's you have a very strong argument for these environments and these software that actually use, doesn't matter what they actually use under the hood, but the interface is much more like it helps you much better, and helps you much more better way to understand how to use these models.
Yeah.
Okay.
And also, I think that just one more thought about that is that when you run agents and agentic workflows, for example, if you just use Cursor, so I think we'll see more and more things that are happening in the background, and it means like more inference, more tokens, and that's just like related to what we'll also cover later. But it seems like the demand for inference is just growing and will continue to grow.
Yeah, but we talked about it many times in the past, right? Like, it's not clear that anyone will make money out of it besides NVIDIA and then maybe Oracle, right? Like, that's good that people are using more and more tokens all the time, but it's not clear that other companies, like the intermediate layers companies, will get something out.
So going off of this, I want to pivot to another kind of news item, and maybe also say that there are a few other companies that are probably going to make money that you might not think about, with Brave being one of them. Like Brave as in the browser, but also the huge index of the web, right? They're seen as one of the primary people that hold the keys to the kingdom in terms of indexed and searchable API for data on the web. Like basically a Google search that AI agents can use. And so I see this fine PDFs data set that Hugging Face, bless their heart, by the way, we in the research space love Hugging Face, right? But they are the largest. They've released Fine PDFs, the largest PDF data set spanning over 500 million documents. And I'm going to prompt this news to my two gracious co-hosts here with the idea that I hear people questioning like how much of the internet has truly been scraped and put into the pre-training data set of the major models. And I hear some people claim it's like nearly 100%, and I push back super hard on this. I claim that the internet is nowhere near being fully mined, and that a huge amount of data exists in things that are hard to parse, like PDFs. So I have not personally like gone through the details of how this was done, but I think that data sets like this serve as some evidence to this idea I have of actually we can keep mining the trash heap and getting more gold out
Yes, I agree. Like at the end, and it looks that so this is an extension of a fine web, right? Like their previous work on how you pre-train, how you take the whole internet, or at least like the available data that out there, and how you manage it and how you filter it in order to make it good for pre-training. And I think like this is so important at the end, right? Like all these like hard things that like that are not, you don't see them anywhere, right? All the big labs and I don't know, even universities labs don't tell you how they actually filter out the data, handle the data. This is the secret sauce of their models. And I think Hugging Face is doing such a great thing here, and they are doing it for few months already, and it's really great because like we need these kind of projects in order to understand how to make models and to make better models and to improve them out of the labs. Yeah, by the way, so if we are talking about data sets and benchmarks, there is a really cool benchmark that I just saw on Twitter. It's called Clock Bench. And basically, it gives you generated several different clocks in like different sizes, different colors with different like shapes and things like that. And ask the models like, what is the time? And apparently, the models don't know it. They don't know how to extract the right time from these pictures. I'm sure, by the way, that till the next version of models, they will know train on this data set. But I think it's a good example of something that looks almost trivial for us. How it can be that these models don't know the time, don't know to extract the time because they know so many things, and like their image understanding is so good many times, right? But still, things that look very simple for us are not easy for models. And we need to train them specifically for these tasks. And like, I'm not sure that, like, of course, that people will say, yeah, the solution is to get better models that will generalize, and that then you don't need to train them for every specific task. And that's true in some extent, but I think like we still need them, like at least in the next years, few years. I believe that we still need to train these models for the tasks that we want to solve. And also, it makes sense because most of our tasks and problems are very specific, and most of the startups, right, they want to solve very specific problems. So you don't need, I don't know, AGIs, models that know to solve everything. You need something that knows how to solve your problem.
I think that if you think about most of the capabilities that by now we think are maybe easy to models, if we want to train for those tasks, then maybe it will be challenging for the models too. So I agree with your point that basically you need to train, but with training, maybe it won't be an issue. So I don't see any fundamental limitations here. Just a train.
Oh, sorry, keep going, Nat.
All good. Just it's a training issue, a training data, if you like.
Yeah, I'm sorry I'm gonna have to put on my I don't know what you call it. I'm not a like amateur watchmaker hat, or not. I'm not a watchmaker, but like I've been shopping heavily for watches recently, and with that, I've also come across some of the other literature around this at conferences that kind of motivated this benchmark. And the core reason that this happens, why image and multimodal models cannot properly tell time based on analog clock, is because on almost every clock listing, like watch listing and related on the internet, they use a very specific, I forget the exact time that's used, but it's the time that basically puts the dials as far away from each other as possible, the minute, hour, and second hand. And so it's something ridiculous too. It's like I think slightly random of a time, but in doing so, most, like, if you ask models to generate a clock, they all have that exact time given, even if you ask them to generate different times, for example. So there's a ton of work that exists about trying to deal with such a heavy pre-training bias that's really like inadvertent, and in this case, I'm sorry, this is if you want to start taking pot shots at like marketing and advertising as bad for society in a mechanistic, like technical way, like harming later things, this is something, you could potentially put in your evidence cabinet here. But absolutely, I love these kind of benchmarks and this kind of work, and this is one of the more interesting of the scenarios alongside like why models can't rhyme. Hey, there's no syllable counting and tokenization. It's like one of those like models are really stunted from the beginning in a way that, you mentioned training. This is such a heavy pre-training bias, right? You have to train on really large data set of very high quality. And so, having probably, I think there was probably a data set associated with that too. It's going to be invaluable. You're going to need many epochs, I claim, of training on that data set to overpower the bias.
Yeah, I'm wondering like how many such buses you have, you know? We basically don't know till we just hit them, right? I just saw someone tweet, I think he was from DeepMind, about like they tried actually, they train on 4chan, and they try to make it like non like as a regular human being, right? Actually, they did it, and the way that they did it is they trained. So they used all the data. They basically pass it through a model, a pre-trained model, and they asked the model to filter out, not to filter out, but like to change the toxic parts of it, kind of adjust the toxic parts, and it works. It worked really good, and they succeed to pre-train, or like to I don't know, intermediate train their model on very toxic data, and to have a normal model that can do very regular things without anything like you can imagine. in- right?
Okay. I'm sorry. I do have to also say I know a thing or two about 4chan, and I have to really caution. I need to read that paper carefully because there are some serious risks to even the approach you've described. I think occasionally, to maybe a lot of times, the detoxic version of whatever somebody said is still probably virulently racist, right? Among other things. Like, I would just say you need to delete that stuff, but I would go even further. If I'm using 4chan as a data set, if you delete all of the boards that are about half that website is just not like not even straight up people being like racist or homophobic or like arguing about politics. A lot of that website is just not suitable unless you're aiming for a certain type of content. And as a result, you can just delete that stuff. I promise you there is nothing your model needs there unless you need reproductive anatomy lessons. As a result, you can do the same thing with the boards that are primarily hate speech. 4chan's a really excellent place on the internet, if not the best place to talk about origami papercraft. I'm not joking. The origami papercraft board is considered there to be like the heart of discussions of origami on the internet. Similar, the cooking board is reasonable. The fitness board is actually extremely influential in the world of bodybuilding. Rich Pinata, Ziz, some of these people. If you care about that kind of thing, you'd know who these people are. So I'll just say that 4chan needs to be treated board by board, and the blue boards, which are the boards where not safe for work content gets you banned, are the boards you should focus on for AI training. And you should probably stay away from things like B, pull, or the other stuff in that genre. Like, just filter it. I'm sorry, like trying to like what you've described, Ravid, is awesome, but I claim that the risk is too high. Ravid, like the model's probably messed up a little bit, and the model is like, oh, I'm normal now, except I think black people are inferior, like that kind of thing, right? But in a non-toxic way, that's what I think would happen from non-careful fine-tuning on all of 4chan, even after going through toxicity detector.
Yeah, I think it makes sense. I'm wondering if we have some good way, to detect these biases, like these biases, and also like just regular biases that we have in our pre-training data. But anyway, like it's very difficult question at the end, right? Like how you detect something that you don't know, and like you don't know even that it's not normal, right? Or like unique, or like not as in the real world.
And it goes back to the clock thing, Alan. You mentioned that all the clocks are on the same time, like points at the same time, do you know what is the time? It's like the sixth finger, right? That you know something, the image is generated. So like, what's the time there?
Exactly. Yep.
Okay. Do you want to talk about other news, or can we go to our main? Okay.
I would support the main event because
Yeah.
I'll just say Nadav here is a certified genius with and at least one oral publication that I got to witness. You, I believe, delivering the remarks on. Sorry, an oral is like a top 1-2% paper within the papers that got accepted, which was already at like 20% acceptance rate of like PhDs and industry professionals. So that's insane, right? Like when I say oral, like even us academics are like, holy, whoa, you're good, that kind of thing, right? So, this Nadav here has had several publications focused on the topic of today and is, I think, widely regarded as one of the foremost experts in the world on it. And so we're blessed here to be able to have you to talk about this topic. And I'd love to hear you just kind of describe in your own words what speculative decoding is.
Thanks, Alan. I really appreciate that. And I'm excited to be here and honored to be here. So thanks again for the invite. Yeah. So about speculative decoding. So I think that perhaps like to start, speculative decoding is an optimization method to make inference faster, cheaper, and so on. But even like to understand that, I think that a step back is like about like the whole like efficiency like thing. So it's trivial that making models run faster and cheaper, that's like a good thing. It's kind of like trivial, but there's a non-trivial effect which the quality can be improved. So basically what we saw about 3 months ago or so, sorry, like something in the past months. So we saw OpenAI and Google DeepMind win the IMO gold medals with their models, and which means the capabilities are already there. They exist. It's feasible. But the reason we are not yet benefit from that as users in our, I don't know, ChatGPT or whatever is that, and that's the caveat, their models had to think for hours. So basically they scale reasoning or thinking, or in RL, sometimes we call it rollout. So they scale that phase, and basically the bottleneck becomes efficiency. So basically it's a question of like how much intelligence can we get per dollar or per second. And if we think more, we see that basically thinking more correlates with a better and a higher quality. So efficiency is not only about making things faster and cheaper, but eventually it also improves quality because we can do more within the same time, meaning like latency or dollar budget.
And so even let's go even like step back, right? Like, so we have these huge models, right? So it takes a lot of time to train them, and it takes a lot of time to run them on during inference. And we can try to improve each one of these sizes, but why not to actually use smaller models?
That's a very interesting question, and the answer is maybe that's the way to go. So I think that what we see, and that's a trend started with the O1 and just continues to grow. Also, not just in proprietary models, but also from DeepSeek and others. So we see test time scaling. We see more reasoning models and reasoning for longer. And what it means, at least like on the inference side, is that we have longer and longer sequences or trees or whatever, but basically sequences. And when you consider this inference, like it has specific characteristics. And basically, when you scale sequences with dense, like standard attention, your bottlenecks becomes actually memory. So the KV cache kind of like grows very quickly, and you start to be bottlenecked by that rather than by the parameters, like the number of parameters in the model, which basically was the way we kind of like approximated or estimated the cost of stuff. So basically we thought about, larger models being like heavier, but basically if you take a smaller model and run it for longer, eventually that would be even slower. Back to your question. So there's an interesting paper. It was released around like 3 months ago from CMU by Beidi Chen and her lab. She's at CMU and also used to be at Meta. And basically they showed, it is called kinetics, and they proposed a new way to do scaling laws. So instead of just considering the model parameter count, they propose a different cost model that accounts for that memory bound issue when we scale test time. So they account for the large KV cache. And basically what they show the Pareto optimal, and what they show that if you take sparse attention models, that's the bottom line, and you run them with more thinking, then you can get better quality, better results under the same latency budget. So basically, if you have just standard attention models and sparse attention models, you can run the sparse with more thinking.
So you mean basically that like we have here, let's say, a trade-off, and it's not clear like even if it's trade-off, but like we have different parameters that we need to take into account, right? We have the model size, we have the sequence size, how much time or like how much during the inference we actually generate the sequence. We have the model type, right? If it's dense or sparse, the attention it's sparse or dense. And there is some mix between all these factors that actually gives you the final quality, right? And also the final efficiency, or like how much time at the end you need in order to generate your solution.
Yeah, and I think that the way people would benchmark like A/B test or whatever different architectures in the past was just to train the same architecture for larger and larger sizes and see how it scales and to find the trend. But that's not accurate enough, because basically the task is that, like the new task of reasoning, we scale the inference time. And basically you want to find architectures that, given some budget, whether it's latency or dollars, they can give you better quality results.
By the way, so what do you think is more efficient, to scale like the inference time or to scale the model? And what is the main factor that will be the most important one?
So it's a good question. I think there's a trade-off, and I think that both are important.
Yeah, I must say that like I personally don't like scaling laws. It's not clear. Like it can give you a good intuition, maybe sometimes, like how the model will behave. At the end, as you say, like, it depends on so many factors. Right? So what does it mean even that like you have scaling laws that depends on I don't know 10, 20 at least different factors? So what you can learn from it, right? Like it's not that you fix one factor, you fix all the others and just scale one factor, right? Like you change all of them and all of them are connected to each other. So at the end, it's not clear to me what we can get from these scaling laws.
And I also want to quickly note that not just do the scaling laws themselves scientifically have that property that you're describing, but that these papers seem to be some of at least the original scaling laws papers, like the chinchilla one and a few of the other later ones. A lot of investors started reading these in the same way that investors started trying to read the DeepSeek V3 paper. I'm sorry, but they didn't get the right lessons from those papers. Those papers are not even like, they were in most cases not even billed this way, but they are not telling you at a certain, like, you only need to go to a certain parameter count and then no higher or things like this. What they're telling you is that at least with the original one, at the initial like dollar for dollar, given the compute that we have today, specifically, not accounting for things like more VRAM in the future, or even, changes in data center design, which can fundamentally affect these things. Like they got really heavily over-indexed as people trying to create ceilings or floors about what parameter counts were needed for certain types of tasks. And I don't think anybody in the scientific community feels confident in saying things anywhere near like that yet. But I'm sorry, I think we're going way off a little bit. I think we still haven't quite gotten to the idea of speculative decoding, specifically the teacher student model, drafter and validator, this kind of concept. I think that mostly what we've been speaking about is motivation for why speculative decoding exists. So I'd love to hear more
Yeah.
about like what this technique is and some of the innovations around.
Yeah, so I think like we understand that this is a problem, like we need more efficient models. So now tell us the solution, how to get there.
So just as a disclaimer, the inference, like it depends what's your objective. If you want to make it faster or cheaper, and the setup. So if we're memory bounded or compute bounded, those are different problems. And what we discussed so far about reasoning, just wrapping up. So when we have longer sequences with more reasoning, we are memory bounded, and that's where speculative decoding shines. So about speculative decoding specifically, so it's an optimization problem, an optimization method that is also lossless. That's like an advantage compared to some other optimization methods, and it essentially uses a more compute in a sense to get tokens faster, in a sense. Basically, it employs a capability that modern hardware like GPUs has, batching, and it uses free batching slots, if you'd like, to run things in parallel. So just in high level, for those who are not familiar, so speculative decoding works in like two steps. We have the first step of and then another step of verifying. And there is a guarantee, a mathematical guarantee, that if you do the verification properly, you preserve the distribution. Meaning, if you wanted to run a GPT-4, you'll still produce tokens that distribute as GPT-4 as if you run it autoregressively. So step, it uses batching future.
And this is the big model, right?
So we have, let's try to summarize, right? The whole idea of speculative decoding is that you can actually make something in parallel, that it's cheaper to verify the tokens versus generate them. Okay, so we are using like small models in order to generate token. We can do in parallel, right? Because we have autoregressive models, so we can do it in parallel. We generate tokens with a weaker model that it's easier to run and like more efficient to run. And we have the verifiers, right? That it can verify in parallel, and we can actually check, like we have a mathematical guarantee, as you said, that these suggested tokens are the same as the original models. Okay, so it sounds too big, too good to be true, right? Like you have a mathematical guarantee to get the same thing as the big model with just a smaller model. What is the catch?
So as you said, the bottleneck is the auto-regressive inference. That's like the standard way to do inference. And basically you take the original large model that you want to infer, and then you have to run a forward pass, and you generate from that a single token. And basically every token that you want to generate, you have to compute another forward pass of that model, and that's expensive. And basically while you run that forward pass, actually you can like compute a batch, and that's like the secret sauce, if you like, and use that batch to do like more stuff in parallel.
So what is the catch?
Yeah, and maybe I'll just another comment is that how we do the drafting, that could vary. So basically you can use a separate drafter model that is faster and run it autoregressively, or you can do other stuff. There are like today, like the common things that we see at VLLM and SGLang, and also Meta and Google are using in production, using a totally separate model. So there are different ways. There's also like This week we just had like another different way to use the target model to do also drafting from Meta, which we might cover later. So basically, I don't want to specify exactly like how we draft, but in the original, most simple version by Leviathan, which is like 3 years ago, yes, we had a faster drafter that we run autoregressively. So now answering your question regarding like how's like this magic, right? Like the verification, how do we guarantee? So basically we use our rejection sampling logic there. So it means just at high level that each token, we consider the tokens, you can think about it like from left to right. Basically, we are searching for the longest prefix, and for every token we either accept it or reject it based on like some a rejection sampling procedure. And in case we reject, we also sample from a new distribution that kind of like fix so I don't want to get like too much into the weeds of like the proof and so, but there is a way using a rejection sampling to basically find the longest prefix of drafts that align with the target distribution in such a way that the target distribution is preserved. And every draft token that we accept reduces a forward pass that we had to do with the target model. So basically, even like so that's like where the speed up is
So
coming.
we have, so just to summarize, right? Like, so basically you generate tokens and now you are trying to verify them and you are doing it with rejection sampling. And if your model is good enough and it generates good enough samples, or like samples that are close enough to the original distribution, then you accept them, right? And if not, you reject them and need to sample more and more tokens, right? And the problem, of course, that if your model, or like your small model, the generate model, is not good enough, so you will reject all the tokens, and on average you will have more tokens that you need to sample in order to get the right token. So it's a trade-off, right? Trade-off between how good your model is, the base model that generate the tokens, right? How good is it versus how small is it? And you need to find the right balance in order to get something that it's on average it's better than the huge model that you don't want to use, but at the same time it align most of the time with this model.
So
Is it true?
sorry.
Is it true?
Yes, right. And the speed up eventually depends on the drafter being sufficiently fast and accurate.
And so, what types of how you can actually like I don't know, evaluate it, or like in practice, what types of drafters you actually use?
Yeah, that's
You
very
just choose one, like whatever, like just random drafter, or like you say, okay, this is like it's smaller one, but it has like a lower quality, and so now I want to use a higher one, but like all these things. How you do it in practice?
okay. So right, those are very two like it's two questions and they're good. So how you evaluate drafters and what drafters people use in practice. So the way you evaluate, eventually, like you want to benchmark on your own tasks. So if you care about throughput or latency in a specific setup, you want to test it in that setup. That's like the ideal way to test, right? So you want to and there are also other ways that are, I would call that like an online benchmarking. So basically you will measure things like latency and throughput, but there are also like other ways to test things offline. You can, for example, you can measure just like the forward latency of specific drafters or just, by their size. And so you can also approximate their latency. And also you can measure their acceptance also in an offline manner. So you don't have to like run it online. Um, yeah, so that's like one way, but eventually you want to make sure that, your throughput increases or latency decreases. And in practice, what people are using, So in practice, it also depends on like what specific setups. But what we see today with, let's say, VLLM, so VLLM just stopped like in their last version 0.10, they stopped supporting separate drafter models. So basically, we used to have like a target model and a different drafter. You can think about like any model from the Hugging Face Model Hub being used as a drafter. But the issue with that is that usually those models are pretty slow, those drafters, and people are moving to use faster drafters. So again, the speed up, the overall efficiency gain depends on the drafter being sufficiently fast and accurate. And
So
what
so now do they have like a list of drafters that you can use?
So what's supported right now, also in SGLang and VLLM, you have Eagle-based drafters. That's like kind of like the standard also in industry, from what I know. That's like unofficial. But so basically people are building this like additional auxiliary head, if you'd like, or something that is very lightweight and its input uh, the inputs of that auxiliary model, auxiliary drafter, could be activations from the target model and things that basically you get from the forward pass of the target. Yeah, so this is one of like maybe the standard way to do stuff. There's also like ngram based drafters that are also, very lightweight. Like you can run them even like on CPU, even if your ngram gets like larger. And they are pretty good at predicting like when you have setups when your responses are copying stuff from your prompt, for example, those are like really effective, at least like empirically. That's like what we know. So those are the like,
And like are there like families of models that we know that are good together as drafters and like now if I want to mimic a Quen distribution, should I use like Quen like smaller Quen or like can I use like other different models and it will have the same distribution?
yeah. So a major issue with using speculative decoding. So speculative decoding, it's like we see that it's effective in practice in standard like workflows, if you'd like the tech giants, they use it in production. And the issue is that like if you want to use it as a developer or like smaller company, then to use speculative decoding, you have to have this like a fast and accurate drafter. And problem is that those drafters are not always available on the hub. In fact, most of the times you don't have a drafter you can use. And one of the key limitations that actually we solved with that like oral paper that Alan you mentioned is that the drafters have to have the same vocabulary. You have eventually it means that you most likely need to train drafters from scratch. And even if you trained one every 2 months, you have a new target model that you want to use, and you cannot reuse your drafters. And that's a huge problem for practitioners, and we solved that problem by basically removing that limitation and let you use any drafter model basically from any vocabulary. So basically you can take any drafter model that was pre-trained already and plug it in. Or if you train one from scratch, you can just reuse it. And there's also an effort, a community effort now to streamline the way drafters are trained, mostly around Eagle drafters, which are kind of like the standard. We have 2 months ago, SGLang launched the SpecForge repository, the SpecForge project, which basically it's a training framework for drafters. Specifically, they focus on Eagle. And also I know that VLLM, I think, have a plan to do something similar.
I'm not sure that I understand. So, like, why you need a specific training framework for drafter? Why? What is special in drafters training?
So yeah, what's special? So you have okay. First, like you like just like implement it, using like let's say PyTorch or whatever from scratch. but they already like baked in some processes that you need. So for example, eventually you train the model to align with a target model. So there's like that's one thing. The way you process data. So there are some like I'm trying to think like basically what's unique and how is it different from other training frameworks that we have. So what training frameworks would you use to train it otherwise, or you just like
I don't know, like any I don't know, any distillation framework or thing like that, right? Like people are doing it all the time. I'm just trying to understand like what is unique in when you want to align drafter.
I think that like there are two things. Like one, yeah, maybe there are like some small differences about like the training. Of course, the objective is a bit different, but that's like maybe not justifying like having like a framework for that. But there's also another thing, and I haven't yet used SpecForge, but I know that it is like focused on SGLang models. So basically, perhaps they are using like that's like just a speculation, like because I'm not sure about that, but like I believe they use like the SGLang like models. So
And what do you think like is the future? Do you think we'll see more and more models like drafter that are aligned to, I don't know, even specific use cases or like specific models and use cases, and like we'll extend it to different scenario? Or do you think like people will not use drafter anymore, just we use like smaller models? What do you think is the future?
yeah. So I think that a few things. First, I think that reasoning is here to stay, and I think we'll see more and like longer sequences and rollouts, if you like. And it means that we are still memory bounded. Yeah, sorry about that. So I think we'll still be memory bounded, and I think that it means that speculative decoding is still it's basically here to stay. I know that there are some users that also would love to pay more to get the lower latency, which is another setup where speculative decoding can help. And regarding the strategies, like speculative decoding strategies that would win, and whether it will be like an eagle or something else. Yeah, sorry about that. So yeah, that's like something that I don't know.
I know interesting. Like I must say that personally, I think like reasoning are a bit local minima. You know that our models went to, because it looks to me very like that most of these reasoning things are unnecessary. And like we can see, right, there are all these like recent studies that show that you can actually remove these like I don't know chain of thought things and things like that. That you can make it much shorter, or like you can even remove them, or like they don't contain a lot of information as we thought they are containing. And I'm wondering if we actually have, you know, if you can incorporate it into the training process, probably like during the RL, that extend these traces much longer than we actually needed. And if we can overcome this problem, it may be that like we don't need we will not be memory bounded, right?
Well, I think that right. So it's a good question. I think that like even before deep learning, if you just like think about like the way people develop chess players with RL, so you don't have deep learning at all. You just have heuristics that used to score different states. So still, like when you do like longer rollouts and you explore your game tree for longer, get like better moves eventually in expectation. So what I'm trying to say is that like same goes for any AI system that we build, and perhaps like the way we're doing this rollout today with the chain of thought, maybe that's like not like the right way, or just like the implementation of it is wrong. But I think that like exploring different futures, that's something that is kind of like found is established.
So I have a question. So Can you do chain of thought, not chain of thought, speculative decoding with chain of thought in the representation space? Coconut style models. That, for example, like people that like if people don't know, like so, coconut is a meta paper from like a few months ago. That basically instead of making chain of thought in the token space, right? That like you generate tokens that are thinking and you feed it them back to the model, you can look on the representation and feed the representation back and make it like this loop in the representation space and not go through the token space. So can you do speculative decoding in the representation space?
Yeah, so there are some works on that, and I think that there's like a lot to explore regarding like how we actually represent not just like a chain of thought, but like in general states and how we use them.
I have a few things I wanted to kind of bring up here. The first is on Ravid, what you mentioned about with issues with chain of thought and reasoning traces. I think even, models are walking the tightrope as they're generating tokens, right? They could be getting in, closer to a solution in some cases by spending more tokens. And we have seen results that more tokens correlate with better performances, at least on benchmarks. But they're also using up their limited effective context window and diluting every additional token as they spend them. And so I view speculative decoding as being valuable, even if we say reasoning isn't an objective that we're, claiming to have improved on, in the sense that for the same model, oftentimes a model is ran by companies where they're utilizing 20, 30, 40% of the GPU, both in terms of memory utilization and in terms of the actual GPU processing utilization, tensor core, all these kind of things. And so being able to turn on speculative decoding and get far more tokens per second for the same model by, it's a little, I hate to use that kind of meme term, but it's like, what if we used 100% of the brain? And a lot of people think that it's like, oh, you get a lot smarter, but in the case of an LLM, it's like you get a lot faster here. And so I think that is independently like this whole reasoning stuff I almost view as orthogonal to just speculative decoding as inference optimization. And going back to what was previously said, pretty much everything else has loss, right? All the other techniques we have for taking a model and making it better or run faster involve in most cases things like quantization or pruning, which are lossy techniques. So having this be lossless and costing basically just GPU VRAM is insane. Like, this is such a cool technique.
Right. You also have some other optimization methods like flash attention and others.
That's also lossless. Yes.
You're kind of like by those methods, like it seems like you're kind of like bounded by the chips, so you can re-implement your kernels to use all the cool new features coming, like I don't know, tensor cores, whatever, and with every like new generation of chips. But then what? And also there are, as you said, you can combine those methods.
And so the LLM inference space continues to be, rapid advancement, in one where software and algorithms can get you crazy improvements. In particular, I'm still influenced by the fact that the DeepSeek folks released so much open source that is still not entirely implemented into I would call it Western developed inference engines like SGLang or VLLM. In particular, things like that specialized file system, I forget what it was called, where it exists entirely to make writes faster. Things like this are part of why DeepSeek continues on their own servers, the company, to be able to run circles around everybody else with their tokens per second. And I'm pretty sure they're doing some speculative decoding in there too. So
I think that there are like so many things we can do to make things run faster and cheaper, but eventually there are a few stuff that kind of like had been the champions or so. And also like last Saturday I went to this Jane Street and GPU mode community hackathon, and basically, those are the guys who were like it's like top talent, kernel developers, and like top talent in general. And basically, like it was like a team competition, and basically we were given like a pre-trained ensemble of models, and we had to make it run faster without hurting accuracy to trade. Basically, the challenge was to trade on all the time, and like as you deploy things faster and you trade more, you gain more. So like it's a very thoughtful way to design a challenge, because you can't win. There's always something that you can improve, and the scores are kind of like continuous in a sense. So it's like a brilliant way to design a competition. And the team that I was part of, we won, and like one of the like key improvements, the thing that gave us like most advantage was batching, which is like, I would say, I don't know if it's like an algorithmic or like a system, but whatever. Like it's not like kernel per se, and you also get a lot from just like PyTorch compile. So basically like another file system, everything like improves by I don't know how much, but like eventually when you think about okay, so at large scale, for example, OpenAI that just like signed like this 300 billion deal to spend on compute. So even if like you can improve like 1% out of that for 5 years, then you're good, right? And there are some methods that do like much more than that, but since like there's so much on stake, so every slight improvement is significant.
And I quickly want to point out that these improvements are at every possible part of the stack. So I think the reasoning stuff you guys talked about is imagining the case of where we want as many tokens as possible spent on one thing. And I always give people the St. Jude Cancer Hospital example, where you might want to put 30,000 pages of text in the input and have the model think for 4 days, because it's still cheaper than a doctor being spent doing a similar amount of work, right? Where there's the other extreme, which you can think of with either, usually it'll be like a military application where you want extremely low latency, right? And also it's often high frequency trading. So in high frequency trading, true high frequency trading happens at the nanosecond scale, and the amount of logic that is being used is extremely low, right? There's very little you can reason on in that space. And so the high frequency trading folks win by being right like 50.1% of the time at that scale. If you can get an LLM or anything close to that, like something a little bit better than one strand of a decision tree, basically like one path at 1 nanosecond, 5 nanoseconds, 10 nanoseconds, etc., like at various closer, like lower and lower latencies, that's huge too. And my understanding is speculative decoding can also, it's as you said, like spend more memory, get faster compute, and thus lower latency, and so every bit of the AI stack is improved here. We kneel to the people who work on this, because it's hard work, improving efficiency with techniques like this.
Yeah, I agree. I think like there are like, so many levels that you can actually try to solve. Like there is the software stack, and like there is the hardware and the intermediate, the kernels and whatever, right? Like we can think about dedicated GPUs or accelerators. I think this is, and every one of these layers like should be combined with other, right? And it should be synchronized with other layers in order to make it. And you have so many, as you said, you have so many different use cases. So there are a lot of accesses that you can try to solve, and you can try to optimize. And I think this is why it's so exciting these days.
And also, I think that like one kind of like a bottleneck or like an interesting thing that is going on is that there is like the open source community is like pretty strong here. And I think that like, we see more and more companies that use SGLang or VLLM as their main inference engine. And it means that, those optimizations, if they are not merged to VLLM or SGLang, then they are not like It depends. Some companies just keep their cards closed and they are not merging, but there are some stuff that like if the engine doesn't support that, then you just like nobody has it. And I think that like one thing that we saw at least like this week coming out of thinking machines, which adopted VLLM as their inference engine, was this reproducibility issue that VLLM has, and also SGLang has. So maybe I just like I can introduce that problem. So basically, the problem is that you don't have full reproducibility with both SGLang and VLLM, and the reason is that you have basically a batching, continuous batching, and it like depend on some different loads, batch size, and so you might launch different kernels, and those kernels might result in eventually different. It has like numerical instability, and basically, if you launch different kernels, you get different results, and those batches are built depending on the load. So basically, you have race conditions, different batches, different kernels are launched, and you get different results. And to control that, that's something that is like so deep in the system today in both SGLang and VLLM that is just too nobody has like a solution today. It's like it's something that is solvable. I learned about it first month ago while I was working on SGLang, and I found out that they have this issue. And then I also found out that VLLM has that issue too. And basically, thinking machines, they propose batching invariant kernels. So basically, they build custom kernels that to guarantee a reproducibility, but it requires more work. We need like more kernels, and there are different solutions to that problem to guarantee a full reproducibility, but every problem has its own issues, and for now it's not something that it doesn't seem like a hard requirement. So basically, you see XAI that use SGLang in production, thinking machines. You have base 10 that wraps VLLM, and no one has full reproducibility, but still like they use it, and
and it works somehow. Yeah. So with this optimistic message, I think we need to wrap up. So, Dav, is there anything that you would like to plug or share with our listeners? I know it can be a good book reading or whatever project that you're working on, and it's very exciting.
Yes. So actually, there's something. So this week we launched a new thing. Basically, we got some co-working space, like in one of the most beautiful places in the city, in New York, just above Grand Central. And basically, we'll do open source there. We'll support like the inference engine open source. So if you work on SGLang or VLLM and you want to co-work with us, it's just like an open space, open source, no string attached. So yeah, message me.
Great. Yeah, so thank you so much. It was great. See you next week.
Thank you so much for having me.